the second derivative. In class, we looked at the story problem where Michael is riding his bike up a hill and then down a hill. And this graph right here shows us how far he's gone in relationship to how long he's been riding. So for the first 5 seconds, he can go a fairly large distance, but as the hill gets steeper, he goes less distance in the same amount of time. We figured out that this was the top of the hill, and then as he starts to go back down, he starts out slow and then he picks up speed so he can go a farther distance and a farther distance. We know that the slope of the tangent line at the top of this hill would be 0, okay? And if we wanted to make an equation for where he's at as far as distance, a position function, it could be this. Now this position function is not perfect because its position at time 0 should be 0, but if you plugged it into the equation, we get negative 6.8, and that's because it's a modeling function. So when we check some stuff down below, it might be a little off, but here's a graph of his position going per time and gives you his distance. If we took the first derivative, okay, ds dt, that would give us the velocity or his speed at each point. And the ds dt right here, at 10 seconds, if you took 0 and plugged it into this equation, it should give you a speed of 0. Now it's a little off because it's a modeling equation, but right now his speed or his rate of change at that exact spot at the top of the hill is 0, and that's going to start to increase again. If you want his instantaneous velocity or his acceleration at that spot, you could take the derivative again and get a formula for that and plug in any time t. Okay? So we have stationary points, or in this case, that top of the hill on the graph was a stationary point where he was moving, he stopped moving for a second and started going down again. Well, there are 3 types of stationary points on a graph: a maximum, a minimum, and an inflection point. And these points are when the slope of the tangent line equals 0. So flat, flat, flat. And there are 3 possible ways to determine what type of stationary point is it. Is it a max, a min, or like our story problem, an inflection point? So the first one is from experience. If you know the picture of the graph, you just might know it. So for example, if my graph was x squared, I know that it's going to be a minimum because I know the graph looks something like this. Okay? The other is by looking at the gradient on either side of the stationary point. So I can maybe look at the slope over here, and this would be positive. Slope over here, this would be negative, which would make it a maximum. Or if this was negative and then this is positive, it would make it a minimum. Or if they were both the same, it would make it an inflection. Okay? And then the third is by using the second derivative, which is what this section is all about. So the second derivative is to take the derivative and then take it again. So we can write it like this, or like this, or like this. And for a particular value, for a particular value for x, what I did was I paused the video and wrote in some rules. If you take a second derivative and it ends up being a number greater than 0 at a specific x, so you plug in x into that second derivative and you get a number greater than 0, we know it's going to be a minimum. Okay, if you plugged in a number and it ends up to be negative, we know it's going to be a maximum. And if you happen to plug in a number and it ends up equaling 0, which would suck, it could be any of those, a max, a min, or an inflection point, so we have to go back to method 2. Now this may not make any sense, so I'm going to show you an example using all 3. Oh, and then here are the rules again. So here's an example using all 3 methods. We need to find the coordinates and the nature of the turning points for this graph. And honestly, I would probably graph it. And so the question is, where are the stationary points? Well, though, the answer to that is, that's when the gradient equals 0. So we're going to find the derivative of the first equation, So dy dx, well, derivative of x cubed is 3x squared. The derivative of negative 12x is negative 12, and the derivative of 2 is just 0. So we have our equation. Now we need to know when is 3x squared minus 12 equal to 0. To solve this, we could factor or solve by taking the square roots. I'm going to go ahead and factor out a 3, and I get x squared minus 4 equals 0. Now if I factored the x squared minus 4, I'd get x plus 4. X minus 4 equals 0. Therefore, the function is 0 when x is negative 4 and 4. So that's going to be the x where I have a stationary point. So therefore, dy dx, the derivative, the slope of the derivative line equals 0 when x equals 2. Or another way to write that, I'm going to show you a couple versions, is f prime of x, or f prime of 2. Oh, I did that bad. Equals 0. Okay. Now we need to know what the y's are at those points. So we're going to go ahead and plug in. I had to pause the video and look. I knew the answer was 2, but I couldn't figure out where I got it. Over here, when I factored this should have been x plus 2, x minus 2. So I'm going to